Alrighty, welcome to Dynamic Programming Lecture number 6. So what did we cover last lecture? So last lecture we talked about finite state Markov chains, and we also talked about things like the Viterbi algorithm and so forth. And so the idea here in finite state Markov chains is, what did you have? You had an underlying state space. Your system was evolving over those states in some form of a probabilistic manner, and here your goal is to try and predict or develop some underlying form of beliefs about where is my state given the information that I have hand. So we talked about this idea of belief propagation. We also talked about this idea of belief propagation conditioned on information that I receive. And here we talked about various different forms of information, such as informations correlated with underlying transitions that my state goes through. And then we also talked about, the last part was maybe not just, we don't just necessarily care about what our belief is at a given instant in time, but we care about our underlying, we care about our evolution. Meaning we would like to understand, given a series of observations, what is the most likely state sequence that happened. Okay? And so what did we demonstrate? We demonstrated that that question about what is the most likely state sequence could actually be cast as a dynamic programming problem, and not just a dynamic programming problem, but rather a deterministic dynamic programming problem, i.e. it's a shortest path problem. So the thing that I hopefully is starting to sink in this class is that many forms of staged optimization problems, right, even those that don't look like it, can all be thought of in terms of the shortest path problem. Okay? And even though we had an underlying system that was evolving probabilistically, what did we demonstrate? Is we demonstrated that the prediction of what's likely to happen, right, or the prediction of where we are, or the prediction of what was the most likely sequence of states that emerged, in fact, was a deterministic staged optimization problem. Okay, so now that we've kind of, I guess, highlighted a spectrum of questions that deterministic dynamic programming can bring to the table or can answer, here now all of a sudden we're going to start bringing in the non-deterministic elements in today, meaning that our state is evolving, but our state is not evolving in a deterministic way. Rather, there's some non-deterministic elements in here. And we're going to ask the question of what can we hope to say there with regard to performance, with regard to policies, and all that stuff. So in particular, what we're going to do is we're going to focus today on worst case dynamic programming. So we're going to try and optimize something in a worst case sense. And then we'll start giving a little bit of a preview for the stochastic setting, where we have an underlying model. We have an underlying model of the non-deterministic elements, and then we try to optimize accordingly. All right, so with that, let's get to lecture number 6. All right, before delving into the non-deterministic elements, their model, and what we're going to try and optimize, I'd like to spend just a single slide kind of reviewing our deterministic dynamic programming framework. So here, what did we have? We had an underlying system, and our system operated in the following way. Our state tomorrow was some underlying function of our state today and our control today. So here our state was representative of x of k. Our state at stage k is x of k, and it's in a set of permissible states, which we denote as capital S of k. Our control decision is represented by u of k, and our u of k is in some set of admissible controls at stage k, which depends on what state we are in stage k. Okay? Notice here I've written x of k plus 1 equals some function at stage k of x of k and u of k. This is just to highlight that the state transition rule need not be the same at day 1, at day 2, and day 3. It can vary, and so here we have a stage-dependent transition rule. Okay, given that, what we've talked about throughout is this idea of coming up with contingency plans. And a contingency plan, what we're going to do is we're going to group all our contingency plans, our policies, into this shorthand notation of pi. So here we're going to denote our contingency plan at day 0 as mu of 0, mu of 1, all the way up to mu of n minus 1. And remember, what's a policy or a contingency plan? Well, a contingency plan at day k is a mapping for each possible state that we could be in at stage k to some form of an admissible control that we could take. Well, what's admissible? Well, each xk maps to a uk, which lives within the admissible set. Given a particular policy pi, right, we can ask ourselves is what is the underlying performance of that policy pi? And so here we're going to evaluate the performance of that policy pi conditioned on our initial state x naught, and that's going to be represented as just j pi of x naught. Well, what is that? That's going to be our sum of stage cost and our terminal cost. So this is going to equal g of n of xn plus the sum from k equals 0 to n minus 1 of g of k of xk. Here we're not going to put in u of k, rather we're going to put in what is the u of k according to that policy. So that's going to be mu of k of x of k. And here, how do we get from x of k to x of k plus 1? We merely employ these dynamics right over here. So what do we have? We have that x of k plus 1 equals some function of x of k and mu of k of x of k. So this guy right here is our u of k. All right, moving along. So that's the cost associated with a policy is this term right here. Now all of a sudden, what are we trying to do? We're trying to do an optimization. So what would we like to do? We'd like to pick the best policy which minimizes this cost. And we're going to note that optimal answer as j star of x naught. So once again, j star of x naught is going to be the minimum over all possible policies of j pi, the cost of that policy starting at x naught. So what did we do? We introduced this idea of value iteration, which is an approach for getting at this optimal solution and the optimal policy. And the way that value iteration proceeded was, what did we do? We introduced something recursively. So we introduced this auxiliary function j of n. And so what did we do? We started off at the last stage, and we initialized j of n for each final state x of n as just equal to the terminal cost. And then what did we proceed to do is recursively went back from j of n to j of n minus 1 to j of n minus 2 and so forth. And we did that according to the following recursion, that j of k of x of k, we minimize over the admissible controls the immediate stage costs, so g of x of k of u of k, and here we could write that also as g of k if we wanted stage dependent cost, or more generally just, or less generally, just g of x of k of u of k, plus j of k plus 1, so the next j at our next state. So once again, j of k of xk is just we minimize over our admissible controls the immediate cost plus the future j. Okay. And what did we observe when we did this idea of value iteration? We had this idea of this principle of optimality. First of all, this recursion led us to the final solution. Okay, so j star of x naught is precisely equal to j0 of x0, which is the ending point of the value iteration recursion. We also had that what? jk of xk is the optimal cost to go at stage k. Okay, it's the optimal cost to go at stage k, meaning that this j of k term actually solves the optimal cost at every state along the way. And hence we'll often refer to j of k of xk as our optimal cost to go function. Okay, and what do we have? Our optimal policy can be derived using this j star, or this j, in the following way. Mu k star of xk is, what is this? This is the argmin over all our possible controls at stage k of g of xk uk plus our future state, the cost of our future state. So once again, what is this? I'm missing a little bit of notation here, but what are we doing? We're minimizing over uk within uk of xk of what? Our immediate cost plus our cost to go of our future state. Okay, so what do we have over here? Remember, this right here is our xk plus 1. So just recapping what these three pieces were, once again, this recursion leads us to the optimal solution, meaning what's the optimal solution? It's this optimization, the cost of the minimum policy starting at x naught. This j also solves all the subproblems along the way, and our optimal policy can be derived from this j in the following way. At each state, at each stage, the optimal policy is just the assignment of the admissible control that minimizes the immediate cost plus our future cost to go. Alright, so now we're going to introduce a variation of this model that brings in these non-deterministic elements. And we're going to enter this non-determinism through our state transition rule. Alrighty, so here's what we have. So our new state transition rule is going to be of the following form. Our new state is going to be a function of our old state, our old control, and this non-deterministic element w of k. So our state at stage k plus 1, so x of k plus 1, is some function of day k of x of k, u of k, and this new element wk, which is our non-deterministic element. So here we're going to have the same constraint that we had before. Our u of k is going to have to live within our set of admissible controls. And what do we have? We have our non-deterministic element now. Our new element is going to be constrained to a set that depends on what the state was and what the control was at day k. So the set of admissible non-deterministic elements is contained within a set that depends on the state and the control. All right, so the question is now, well, how do we evaluate the worth of a policy? So if we specify an underlying contingency plan, how do we account for these non-deterministic elements in our underlying evaluation of the cost associated with the policy? Okay, to that end, here's what we're going to do, at least for today, is we're going to think about things from a worst case perspective. So the cost associated with an underlying policy, pi, starting at x0, which once again we're going to keep the same notation that we had previously, is going to be j pi of x0. Well, we're going to evaluate the worth by thinking about, well, how bad could that cost be for the worst possible disturbances? So we're going to do a maximum over all w0, w1, all the way up to wn minus 1 of our terminal cost plus the sum from k equals 0 to n minus 1 of all our stage cost. And once again, here what do we have now is our stage cost is now a function of our state, the decision, and now this non-deterministic element. Okay, so we've seen now that this non-determinism has entered in several parts. This non-determinism is entered in our state dynamics over there, and it's also introduced in our stage cost over here, and we've also factored it in to our underlying objective right there. Okay, so once again, how are we going to evaluate the worth of an underlying policy pi? Well, what we're going to do is we're going to look at, well, how bad could it be with the worst possible disturbance sequence of what? Of our terminal cost plus the sum of our stage cost. So now what is our goal? Once again, we're thinking about optimization. So what are we trying to do? We're trying to choose our policy that minimizes our cost. So we're going to denote j star of x naught to once again be the minimal cost over all policy of j pi of x naught, where once again j pi of x naught is looking at a worst case performance, meaning what's the highest the cost could be for any possible disturbance. Okay, so j star of x naught really is trying to find our contingency plan that minimizes our worst case cost. So once again, what's our new element here is we have this idea of adversarial disturbances. What are we trying to do? Disturbance is going to seek to maximize our cost. Control commits to policy before disturbance acts, and that's modeled in this idea that the set of admissible disturbances is allowed to depend on our underlying control policy u of k. It's very different from control that commits to actions. Okay, and disturbances can be constrained by state and control, and once again that's captured over here. That's our underlying model. Now, why is our motivation, or what is our motivation for studying this? Well, there's several, but at first is, well, what if we don't have an underlying model of how our non-deterministic elements are going to behave? Well, what does this do is this gives us design guarantees and verifiable performance, meaning if we can optimize worst case guarantees, what do we know? We know that for any realization of disturbances, they must be better than these worst case guarantees. And it also starts paving the way for this idea of strategic interactions, meaning maybe our disturbances are not acting in a suboptimal or not acting according in a worst case perspective, but at least provides us guarantees in that realm where maybe they're operating according to some other strategic objective. All right, let's look at a few examples of where these worst case guarantees might be a reasonable way to proceed with an analysis and a derivation of an optimal strategy. So the first example that I would like to think about is this idea of disturbance rejection. So consider the case where we have the following dynamical system. X of k plus 1 equals A times x of k plus b times u of k plus L times w of k. And for this sake, let's imagine that our disturbance wk is somehow something bounded less than or equal to 1. Okay, so the absolute value of this is less than or equal to 1. If we think about this being, integer values, this could be minus 1, 0, or 1. We just don't know, and we've already seen an example of this in lecture. Okay, so here the question then centers on if we don't know what w of k is, okay, and we experience some form of a cost. Let's imagine our cost is some function c times x of k. Okay, so that maybe that is our output. So we penalize our output, or the size of our output. We have this underlying form of dynamical system where we don't have an understanding of what w of k is. It's non-deterministic, but we have bounds on how big it can be, or bounds on the absolute value. So what could we want to do here is, well, one might think about trying to minimize a cost from a worst case perspective. So what does that mean? I would like to choose the minimal policy. Pick the policy which minimizes the cost. Or how am I going to evaluate the cost of a policy? Well, I'm going to look at the worst possible disturbances that can act upon the system. And maybe what I'm going to take is the peak output that is realized. So what is this doing, right? This is trying to find the policy which minimizes the worst case peak output. Okay, that's one illustration. One could have this be cumulative, but this is one example of a worst case objective. Maybe I care about what the peak output is, and here, so I want to minimize the worst case peak output. All right, let's look at another example. And so here we'll focus on this idea of switching systems. So here, once again, we have a dynamical system where x of k plus 1 equals a x of k plus b u of k. But suppose that I don't understand what my A matrix is. So what do I mean by that? So we're going to imagine that our adversary, or our disturbance, chooses the underlying A matrix from a collection of possible A matrices, A1 through AN. So once again, what are we having here? We're having that the new state is equal to the A chosen by the non-deterministic element times x of k plus b u of k. So I don't know how my state is going to evolve. Why? Because the adversary, or a non-deterministic element, is choosing the underlying state dynamics, or the state transition matrix A. Okay. So the question is now, what would we try and do here? So if I don't have a model for how the non-determinism is going to select from this A matrix, maybe what I care about here is, once again, minimizing worst case guarantees. So what does that mean? I would like to choose the policy which minimizes the worst case cost. So here what we're going to think about is minimize over all, for each policy, the cost associated with policy is going to be, here we're going to stick with the peak output. So here it's going to be, what is the worst case peak output going to be? Okay, so minimize over policy, so find the policy which yields the smallest possible peak output. Or let me state that one more time. Find the policy which minimizes the worst case peak output. Okay, notice here throughout, what did we do over here is we had a model where just our non-deterministic element, the absolute value was bounded between -1 and 1. Right here we had, another case where, our non-deterministic element could be anywhere within that set. And one could come up with far more sophisticated disturbance models. So for example, we could have an underlying disturbance model where the disturbance at the ensuing time must be somehow close to the disturbance at the previous time. And here this measures how close it needs to be.
So here the idea is we're thinking about things in a worst case sense. We can get more sophisticated if we want to and do worst case over these more sophisticated models. But here the idea that we're trying to get across today is just that these worst case guarantees and what they actually mean. And so here when we think about disturbance, these really need not be adversarial. So when we're thinking if we're trying to do disturbance rejection, it's not necessarily adversarial, but this worst case formulation provides us underlying guarantees irrespective of model. So it removes model from the equation altogether. Like if we don't have a good understanding of the model associated with the underlying disturbance, we can just view it or treat it as adversarial, derive the best case or derive the optimal policy given that view, and then what? And then at least we know, irrespective of what our underlying model is, these worst case formulations provide some level of guarantees. While worst case analysis provides guarantees irrespective of the underlying model of the non-determinism, there's many cases where one might want to impose a degree of structure on that, meaning that the nominal setting of where we just do worst case over everything is a little bit too broad to give us meaningful results. And so here are two forms of structure that we'll consider as this idea of rational and also some form of adversarial. So let's take a look at an example. So here what do we have? We have a pursuit evasion problem where the state of the pursuer evolves according to a linear system of the above form, P of k plus 1 being the state of the pursuer at time k plus 1 is equal to A of p times P of k plus B of p times U of k, where U of k is the input of the controlled pursuer. So this defines the set of possible state trajectories that the pursuer can follow, driven by this underlying control U of k. Okay. Likewise, the evader has a given linear system which dictates the evolution of its state. In particular, E of k plus 1 equals A of E times E of k plus B of E times W of k, where WK, once again, is the control input here to the evader. So the idea here is when we think about an evader and we model an evader's dynamics according to this form of a linear system, this defines, in essence, the space of possible evader trajectories. Okay? So here now, rather than doing a worst case analysis, one can do a worst case analysis where we restrict attention to the set of state trajectories of this form. So here, for example, one objective could be to try and minimize the distance between the evader and the pursuer at some instance of time, let's say time k. We could envision several other objectives of this form, and here what the pursuer would like to do is to choose a contingency plan such that the worst case adversarial policy in this form tries to minimize this. So what do we want to do once again is we want to choose a contingency plan which minimizes the worst case distance we're away from the adversary at some time k, where we do a worst case over all adversarial policies of that form. All right. Okay, so there's others. So here all that we did is we strapped an underlying model, so we didn't do worst case over all possible trajectories. What we did is we did a worst case analysis over all trajectories of this form, where trajectories of this form were in some sense deemed reasonable in our mind. Okay, so we could consider other versions as well, such as strategic games, right? So here if we're playing an adversary in some form of a strategic game like chess or Go, is a worst case model really the right way to go about things, or should we assume some level of rationality? Now, to highlight the difference, let's look at this idea of something called a centipede game. So here's a centipede game. A centipede game is a two-player game, and players alternate in making decisions. Okay? So at first, player one is tasked with making a decision. Okay? And this player has two choices, either to quit, okay? Either to quit or to choose to continue. Now, if the player chooses to quit, the player earns a payoff of 1, and the payoff to the other player is deemed as 0. So when I write payoffs like this right here, the first component of that payoff will be the payoff to player 1. The second one will be the payoff to player 2. So once again, player 1 is faced with a decision. That decision is either to quit immediately, at which point player 1 gets a payoff of 1, and player 2 gets a payoff of 0, right? Or to continue. At which point, if that player chooses to continue, then all of a sudden, the decision goes over to player 2. Okay? And player 2 is faced with the same issue. The player can either choose to quit or continue. And in this particular case, if the player chooses to quit, the player is going to get a payoff of 1. And the player, what do we have over here? We have player 1 will get a payoff of 0. Okay, so once again, player 1 or player 2 is now faced with the decision to either continue or quit. If player 2 decides to quit, the payoff to player 2 will be 1, and the payoff to player 1 will be 0. All right, then the process keeps repeating. So if the player chose to continue, then all of a sudden the decision goes back to 1, who's faced with the decision to quit or continue, at which point, what do we have over here? We're going to have that the payoff would be 2. Here. Meaning that what? Let me take a look at that. So what does that mean? If at this stage, player 1, so once again, it's player 1's decision right over here, chose to quit, the payoff to player 1 would be 2, the payoff to player 2 would be 0, right? If the player chooses to continue, then all of a sudden it would revert back, the decision would revert back to the other player again, and we'd get a payoff structure that looks like this. Okay, so meaning that, once again, what would happen in this particular case is a payoff to player 1 would be 1 and 3, and so forth. Okay, and let's imagine that it would terminate at the ensuing time step. Okay, so, and at this point in time, if we ever make it to that stage, it's quitting automatically. And so here, let's call this guy 1 and 2. Okay, so let's try and ask ourselves what form of behavior, or let's call this actually 2 and 2. So let's ask ourselves what form of behavior would actually emerge in this setting. Okay, meaning that once again, if they continue to the very end, each individual is going to get a payoff of 2. Okay, and so clearly that makes sense. Let's understand whether or not that would happen. Okay, so to do that, what I want to do is I want to analyze each one of these subgames. And let's say for the moment that we start in this last state. Well, if we start in this last state, there's no decision to make. What are we going to do is we're going to get a payoff of 2, 2 to the individuals, meaning both players are going to get a payoff of 2. Okay? So now we're going to try and ask the question of, well, suppose we're in this state right here. Okay, what should player 2 do? Player 2 has a choice of continuing. If continues, the payoff will be 2, 2. If the player quits, the payoff will be 1, 3. So one can ask the question of, well, what do we want to do in this domain? Well, from player 2's perspective, if player 2 is rational, right, and thinking about things, well, if he quits, he gets a payoff of 3. If he continues, he gets a payoff of 2. So what does that mean? That means the best case situation is to quit, which means that the payoff to the players in this particular case is going to be equal to, sorry about that, it's going to be equal to 1, 3. Alright, so then we can go back one more step and we can ask ourselves, okay, if we're here, what's player 1 going to do? And so what do we have? Well, if the player chooses to quit immediately, there's a payoff of 2, 0. If the player chooses to continue, it's going to be 1, 3. So from player 1's perspective, if he quits, gets a payoff of 2, continues, gets a payoff of 1. So clearly what's going to happen over there is we're going to get a quit, and this is going to garner a payoff of 2, 0. Likewise, if we're in this situation, if we move back one more, right, we can follow the same form of logic, and what's going to happen over here, we're going to have this idea of a 0, 1. Player is going to quit immediately, and likewise, if we go over here, player is going to quit immediately. Okay, so if we want to start thinking about, well, what is an underlying rational model, or one can start arguing about underlying payoffs. And the idea here is that even though them continuing to the very end yields a higher form of payoff, right? The idea here is that, well, given this model, players quit right away, right? So here, once again, rational model of opponent forces you to immediately quit, even after observing multiple missed time steps. What does that mean? Even if we got to, let's say, right over here, So we saw that player 1 was not acting rational at first, player 2 would quit right away. So the idea here is when we have all these different forms of underlying models about rational, worst case, we also have to understand their underlying implications, that they don't always yield, in some sense, predictive behavior. Nonetheless, and somehow we need to, when we're doing worst case, we need to somehow benchmark something against something, right? We need to try and come up with an underlying policy that tells us something about the performance of our policy relative to some underlying model. Worst case is one, rational is another one. We just have to understand that there might be limitations or kind of pathological issues that actually emerge that don't always make sense. All right, so the question now is, well, how do we solve for an underlying optimal policy in looking at these worst case styles of guarantees, or these worst case models? So once again, what is our underlying setup? Once again, we have state dynamics, x of k plus 1 equals some function of x of k, u of k, and wk. So now we have our non-determinism once again in our state dynamics. Our set of admissible controls is now dependent upon our underlying state, and our set of admissible disturbances is now dependent upon our underlying state and the control action that we took. So these are the primitives. Okay. So once again, now what is the cost of a policy pi? Well, j pi of x naught, the cost of a policy of pi, is, well, let's look over the maximum set of disturbances that can hit our system of, once again, our terminal cost plus the sum of our stage cost. So the sum from k equal 1 to n minus 1 of g of k of xk, mu k of xk, wk, where once again, now our stage costs depend on our non-deterministic element. What is our goal here? Our goal is to solve for j star of x naught, which is, what is that? That's going to the minimum policy, the policy which minimizes our maximum cost, right? So j star of x naught is defined as the minimum cost achievable through a policy pi of j pi of x naught. Okay? All right. So the question is, well, how do we get at this? And what we'll see is that we have something very similar to what we did in deterministic dynamic programming, is we have this idea of value iteration. So what are we going to do is we're going to initialize jn of xn to equal our terminal cost, right? And then we're recursively going to define j of n minus 1, j of n minus 2, etc., according to the following recursion. jk of xk is going to be defined as the minimum overall uk within our admissible set, the maximum overall wk within our admissible set of our immediate stage cost plus our future cost to go. Okay, so once again, jk of xk is going to be defined as the minimum over all the control actions we can take, and then for each control action we're going to look at the maximum disturbance that can cause with regard to maximizing our immediate stage cost plus our future cost to go. Okay, so this is our recursion, and so when we have a min-max in order like this, left to right is basically the order of commitment. So here what happens is we set u and we allow w, our disturbance, to be dependent upon u. Okay. Now if we follow through with this recursion, we get the following guarantees. First of all, the ending point of this recursion, j naught of x naught, is precisely equal to the solution of our underlying optimization problem, the minimum cost attainable, where we evaluate the cost of a policy, once again, by what's the worst that the disturbance can do upon it. Okay, so this recursion leads to the solution. Furthermore, this recursion also gives rise to what is the underlying optimal policy. So here, the optimal policy at state xk at stage k is precisely equal to the argument u that minimizes within our set of admissible controls. So the uk within our set of admissible controls that minimizes this cost right here, which is basically minimizes the maximum cost that's attainable through disturbances within this set. So for each uk, we're defining this quantity to be what's the worst that the immediate stage cost plus the future j can be. And so here what we're trying to do is we're picking the u that minimizes that combination. Okay? So once again, this recursion of value iteration, where we initialize our j of n is just our terminal cost, and we proceed to define each j of n minus 1, j of n minus 2 recursively according to this equation, yields us the solution to what we were originally after, and also gives us the underlying optimal policy that achieves that. All right, so we introduced a version of value iteration, and all that we merely stated was the underlying theorem that value iteration actually works when we view this idea of worst case non-deterministic elements. So when we look at things from a worst case model. Now we haven't proved that yet, and that's where we need to go, but before going to that, we need to prove some underlying properties about what these max-min style equations look like, okay? And what type of properties we have. And so to do that, what we were going to do is we're going to take a break at least from this for the moment and just focus on max-min, and in particular we want to illustrate this property called the minimax inequality, okay? So here, let's imagine that we had an underlying function, g of x, y, where x lives in some set and y lives in some set. So here all that we do is you could think about this being an underlying matrix where x is the row, y is the column. Just the key is we have a function that depends on two underlying parameters. Okay? And we want to start exploring some relationships about the min-max, meaning we're going to minimize over x and maximize over y, versus the max over y, min over x of the same function. So here, once again, we want to start studying the order of operation and what its implications are. Okay, so what did we talk about? We talked about this when we have a min-max, it's commitment. And the commitment goes from left to right. So what does this mean? It says first we choose x, then y is allowed to depend on x. Okay, over here we first choose y, and then x is allowed to depend on y. Okay, so that's kind of the order of operations in these max-min and min-max formulation. Okay, so the first property that we want to highlight is this idea called the minimax inequality. And what is that saying? That the min-max, min over x, max over y of g of xy, is always greater than or equal to the max-min, where we do a max over y, min within x of g of xy. Okay, so the minimax inequality says that the min-max of a given function will always be greater than or equal to the max-min of a given function. All right, so let's try and inspect why that is indeed true. Okay, so what do we have over here? So let's take any particular xy, and let's evaluate what is g of xy, and let's put that guy right there. Okay, so one can start to ask the following questions. Okay, well, if x is given, how big could g of xy be? Okay, so once again, if x is given, how big could g of xy be? And that could be directly written as the max over y of g and x of xy. So once again, this is precisely given x, what's the biggest that g of xy could be? And by definition, this has to be greater than or equal to g of xy. It could be equal if this y was already the biggest that it could be, but in general, this could be bigger than that. Okay? Likewise, what we can start to ask over here is, well, given y, what's the smallest g of xy can be by varying over x? And so that's defined as just the minimum over x of g of xy. So, and what do we know? This must be smaller than g of xy. Alternatively, g of xy must be greater than or equal to the min over x of g of xy. Okay, so notice right over here that this term on the left is just a function of x, purely a function of x. And so we can write that as just the left-hand side of x, just a function of x. And what do we have over here? The right-hand side is merely just a function of y. Okay? And what did this show is this function of x is always greater than or equal to this function of y. And so this function of x, we can ask ourselves, well, what's the smallest this function of x could be? Must always be bigger than the biggest that this function of y could be. And we could express that in the following form, that the minimum over x of the left-hand side of x must always be greater than the max over of y of the right-hand side of y. Okay? And then if we look, we notice that that's exactly this expression over here. This is purely a function of x. This right here is purely a function of y, and that gives us our minimax inequality. All right, so the first thing, once again, is just recapping the minimax inequality. If we have a given function g of xy, the min over x, max over y of g of xy will always be greater than or equal to the max min of g of xy. Okay. Next is we could start thinking about minimax exchanges. And so here things are going to be a little interesting, is rather than committing to a particular choice of x, rather we're going to rely on an underlying function. We're going to commit to a function which maps w here to u, which is taken on our term of x. And so it says, okay, well, suppose that rather than thinking about minimizing x, we rather thought about minimizing a function that took in a y and returned an x. Okay, so what's the minimum function mapping w to u? So here we'll write this, the maximum over w of g of mu of w comma w. So once again, all of a sudden, we're not committing anymore to a particular choice. We're committing to a mapping from w to choice. Okay? And it turns out that here, what did we talk about? We talked about, well, ordering mattered, right? Right is able to condition their choice on left. But here, what is effectively happening is that left over here isn't specifying a choice, it's specifying a rule, right? And what this rule means is that effectively we lose the disadvantage of going first. So by committing to a function first, what do we know is we don't have that same disadvantage. So what do we know is we know that the min, or the fact, and this is referred to as the minimax exchange, the min over functions, the max over w of g of mu of w comma w is precisely equal to the max min in this case, where max min is now in terms of actual choices. Max over w, min over u of g of uw. All right, so let's see why this is true. Okay, so the first thing that we can do, what do we know? Is we know that the min over mu max over w of g of mu w comma w always has to be greater than or equal to the max min, max over w, min over mu of g of mu w comma w. Right? Where does that come from? That just comes from our minimax inequality. So all that we did is go from min-max to max-min, kept everything the same. Now notice that over here, min is over policies. But remember, when we're the inside min, we get to observe what the outside did. So here we don't need to restrict our attention to policies anymore because we know the specific w that's been implemented. So here, this guy right here is precisely equal to the max over w, min over mu of g of mu comma w, just due to the fact that we don't need to rely on functions over here because the inner min knows exactly what the outer one chose. Okay, so what does that give us? That gives us at the end, we have min over mu max over w of g of mu w comma w is greater than or equal to this quantity over here, which is the max over w min over mu of g of u comma w. Now, so here we have inequality, that this guy is greater than or equal to that. To show equality, all that we need to show is derive a specific mu star that does that. And here the mu star that does it is mu star of w is just equal to the arg min of u of g of u comma w. If we plug this individual into here, so choose that one, we get that this guy is precisely equal to that one. And that shows the inequality. All right, so now that we have some understanding of this min-max and there's max-min, and we know things like the minimax inequality, so the question now centers on, well, how can we go ahead and prove that value adoration actually converges to the right answer in these worst case style of formulations? Okay, so what do we have over here? Let's just take a look at the special case for n equals 2. So we'll do a two-stage optimization problem where we focus on minimizing the worst case kind of performance guarantees all right, and so let's think about how to progress with here. So given that n equals 2, is what can we do is, well, we can initialize our underlying cost to go at stage 2 to just be equal to the terminal cost for all possible states. Okay, excellent. Now introducing our recursion, what do we have? J1 of x1 is going to be defined as the minimum over all admissible controls, maximum over all disturbances of our stage cost plus our J2 of our next state. All right, so once again, our recursion is just that form, J1 equals min over U, max over W of this individual. Okay, and so if we write down what our J star of X naught is, the solution of our underlying optimization, well, this is precisely going to be equal to min over our policy at day 0, min over our policy at day 1, so min over both our policies, max over both non-deterministic elements that can hit our system, of some underlying cost, and here I'm just not going to express this out in its totality, but some underlying cost, we'll call that cost G prime, that depends on mu0, mu1, w0, w1, conditioned on starting at x0. And if we wrote this out, this would be the sum of our stage cost plus our terminal cost, but here for simplicity, let's just write that as G prime. Okay, so what one could do is one could also think about absorbing all these guys into a new function and call that function G. So let's see what I mean by that. So what we could do is let's define a function that depends on mu0, mu1, and w0 and x0. So right here, we're finding this function G, which is going to be defined as the max over w1 of G prime of mu0, mu1, all the way up to x0. So all that we're doing is we're moving w1 and we're absorbing it into this mu function, G of mu0 of mu1, w0, and x0. Okay? So all that we've did was absorb it. Right? We've just pulled out one component of that, the w1, and we've implicitly defined that in that function G. So G doesn't depend explicitly on w1, rather it's implicitly where we do a w1 as a maximum over all these guys. Okay. So if we're now thinking about solving for J star of x naught, given our definition of G, we can now recast that as the underlying optimization of min over policies at day 0, min over policies at day 1, max over our non-deterministic elements at w0 of G of mu0, mu1, w0 conditioned on x naught. Once again, we've pulled w1 out of the equation just by absorbing it into our definition of G. So what do we have here? Note that when x naught and mu naught are specified, okay, x1 is effectively just a function of w naught. Okay, all right. So let's think about applying our minimax exchange and restating G prime. Okay, so what do we have over here? Is what do we have? Min over mu1, max over w0 is what do we see is that by our minimax exchange, what do we effectively get is we get min over mu0, max over w0, min now over u1, right? By our minimax exchange, remember, this was a function, right? This was a function of purely, effectively, w0. And so what can we do is we can just reverse them, and now rather than having a function here, we can now have the actual u that we're having. Okay? So, and then substituting back in w of 1, we have this guy. Okay? So by applying the minimax exchange and restating G prime, what do we have? We now have transferred this optimization to this one. So min over mu0, max over w0, min over u1, max over w1 of G prime. Okay? So this definition is precisely the same as over here. All that we've used is the minimax operator, or the minimax exchange, to show that we could swap these two in this way. Okay? So what does that mean? Is that all that we need to do now is, what do we have over here? Well, we know what this guy is. Min over u1, max over w1. We know exactly how to compute these last parts, absorb those in together. So what we can effectively do is just expand the definition to show precisely what we have over there. J naught of x star, or J naught star of x naught, is precisely equal to the ending point of the recursion. So once again, when we wrote down our underlying definition of J naught of x star, we had this guy, right? And in particular, look at the ordering. We had min over mu1, min over mu0, min over mu1, max over w0, max over w1 of some underlying cost. Well, what did we want to do is these two were in an order that we didn't know how to deal with in terms of dynamic programming. So what did we effectively need to do is to reverse them, right? How did we reverse them? We invoked this idea of the minimax exchange. So we wrote out this definition. We noticed these two individuals over here exactly followed the minimax exchange that we had on the previous, and so we could swap them. And not just swap them, but rather than put a function here, put actually an output over there. Okay, and now all of a sudden we know how to handle min of u1 max over w1. That's precisely just this equation over here. So once again, one can take out this, throw in j of 1. By looking over at these guys, then all of a sudden, what does that mean? We're throwing in now, repeating the same logic, we become j of 0, and we get the recursion that emerges out from here. Okay, so once again, all that this slide did was go through a special proof in the, that value iteration when we look at worst case models actually gives us the right answer as well. We couldn't take it for granted, one needed to prove it, and here we relied on the minimax inequality and the minimax exchange to be able to give us that result. All right, let's put an example that kind of brings everything together. And so here what I want you to think about is this idea of a scalar linear system where we have some form of a linear system governing our underlying state. So our state tomorrow is equal to our state today plus the control that we took today plus the disturbance that we could take that's taken today. And here let's imagine that the disturbance is bounded. The absolute value is bounded. It's less than or equal to 1. So here disturbances can take any value between -1 and 1. So here we're going to assume that we have a stage invariant cost of the following form, the absolute value of x plus 3/2 times the absolute value of u. So you're penalized for your state being away from 0. You're also penalized for the control that you take. And here what we see is control is a little bit more costly than state. Okay. What do we have? We have a terminal cost that just depends on the magnitude of my state, how far away my state is from 0. And here, let's imagine that we're just looking at the case n equals 2. Okay, so let's see how we're going to proceed. And with this, we're going to have to start making arguments about what is the structure of the worst case disturbance and what is the structure of the optimal control. We might not kind of be able to always enumerate everything like we've been doing before. Okay. So starting over at stage 2, this is the easy one. We're going to initialize our cost to go at stage 2. For x is just equal to the absolute value of x of basically how far that we are away. Okay, let's proceed back to j1. And once again, what is the definition of j1? j1 of x is going to the minimizer over u, maximize over all disturbances, less than or equal to 1, of what? The absolute value of x, plus 3/2 times the absolute value of u. So once again, this is our immediate stage cost, plus this right here is our future cost to go. So that right there, just to make sure we're all on the same page, this guy right here is j of 2 of x2, and recall x2 equals x1 plus u1 plus w. Okay. All right, so that's where we are. So j1 equals all those. Well, so here, what do we have to do? We have to make some form of arguments about what w could be, right? W can take on any value between, -1 and 1. But if we start thinking about this, can we simplify it more? Do we have to consider all those possible? And if you think about it, well, what w should be if w is trying to instill the most cost on the system? Well, w is going to be directly aligned with what x plus u is. So in particular, if x plus u is positive, then w is going to be +1. If x plus u is negative, right, then w is going to be -1, right? And what that allows us to do, what that insight allows us to do is effectively to scratch this, x plus u plus w. In a worst case sense, this is going to go to x plus u plus 1 with that appropriate choice of w. So here what we can do is we can substitute that into the equation through this recognizing the case that w is aligned with x plus u, and here we're going to get this form of transformation that comes into play. All right, so given this form of transformation, it's also quite easy to see we have some form of a linear relationship. In appropriate regimes, obviously, we have this, the absolute values. But what do we have is the best case u is going to be at a vertex. Right? We don't have a set of polynomial equations where it could fall in between. Really, it's going to be either at 0 or at minus x. There's no other ifs, ands, or buts about it. That's where the optimal point is going to lie. So here what we can start doing is, rather than structuring over all or looking over all possible u's, is we can just actually look at the vertexes at either u equals 0 or u equal minus x. Okay, so if u equals 0, what is our underlying cost? Well, we pay a cost of the, of the state, so cost of the state, plus 3/2 times the u, so plus 3/2 times 0, so 0, plus our emergent state, but remember we're able to introduce this as a surrogate, as this would be the worst case disturbance. So when u is equal to 0, our emergent state is 1, so we get a plus the square root of x plus 1. Okay. So this is when u equals 0. Let's also analyze the case when u equals minus x. So what do we have? We have, once again, the absolute value of x, plus 3/2 times the absolute value of x again, plus now what is this guy? X plus u equals 0. So what do we know? We know that this guy equals 0, so we just inherit a 1 over there. So what do we get when we just simplify these guys a little bit? Is we get what? We get that the top one equals 2 times the square root of x plus 1. The bottom one equals 5/2 times the square root of x plus 1. So what do we get? The winner, or the smaller one, is precisely equal to this one. So what do we have over here? We have j1 of x is precisely equal to 2 times the absolute value of x plus 1. And what's our optimal control? Our optimal control is to do nothing. Set u equal to 0. In particular, investing the cost to lower the state is not worth it, because effectively the cost of applying that control is too high. All right, so perfect. So we've established what j1 is, the explicit form and our underlying optimal policy. Do nothing. All right, let's go ahead and go back to j of 0. Okay, so here I have this. So once again, this guy is j of 0. All right, and let's see what we have over here. So once again, j of 0 is minimize over u, max over w less than or equal to 1. Of once again, our stage cost is the absolute value of x plus 3/2 times the absolute value of u. Plus, now we're going to have to substitute in what j1 is. So plus 2 times the absolute value of x plus u plus w, plus we're going to inherit this extra 1. Okay, so let's think a little bit about what do we have over here. Right, this, remember, recall, is that this right here is precisely equal to that guy over there, which is what j1 of x1. Okay, so that's just instilling our definition. Right. So what we can start to do is we can start to reason about things in much of the same fashion. What do we have is the worst case w is going to be aligned with x plus u. That much is clear. Right, and we also have the case that when we think about things that, the best case u is either going to be at a vertex. We're either going to be looking at u equals 0 or u equal to minus x. All right, so let's look at the cases. When u equals 0, what's j naught of x going to be? Well, it's going to be the absolute value of x plus 0 plus 2 times x. Here, the worst case w is when it's aligned, so we can pull that out. But we're going to have to multiply that by 2, so we get a plus 2. And then we get this extra plus 1 on the outside. Okay, so what do I mean by that? When I said pull it out, what do we have is this 2x plus u plus w. When we're looking at the worst case disturbances, w is going to be aligned. It's going to be aligned with the direction of x plus u, meaning if x plus u is positive, w is going to be positive 1. If x plus u is negative, w is going to be negative 1. So when thinking about worst case, what do we have over here? This guy's just going to lead into x plus u plus 2. All right, so when u equals 0, what do we have? Absolute value of x plus 0 plus 2 times the absolute value of x plus this extra 2 that comes from our disturbance plus 1. Okay. When checking the other case, when u equals minus x, what do we get? We get the absolute value of x plus now 3/2 times the absolute value of x. Now what do we have? X plus u is equal to 0 in this particular case. So what do we have? We're going to have this just going to be plus 2 plus 1. So if we add up all these, what do we see? We see that this top one equals what? Equals 3 absolute value of x plus 3. What do we see? This next term equals, what do we have? We have 5 halves absolute value of x plus 3. So what do we see? This one is our optimal choice, and this one then becomes our cost. So recapping, what do we have over here? J naught of x equals 5 half times the absolute value of x plus 3. And here our mu naught star of x equals minus x. Okay? So notice that what did we have here is when we just had one stage, right? Reducing the state was not worth the underlying cost. However, when we had 2 stages, all of a sudden investing that energy early on, even though we paid a price, actually turned out to be beneficial. So this problem starts to go through and start thinking about when we're going to be looking at staged optimization problems, we're quickly going to move away from just exhaustive enumeration, right? And we're going to have to make some degree of arguments as to what's happening. And that's what we did here. All right, so the previous example highlighted some of the challenges associated with running dynamic programming when looking at this idea of worst case models. Okay, and so the homework that you're having will also bring a couple of those to the forefront as well. But moving on from that, right, in many systems there's this idea of random phenomenon. We've talked a lot about that in terms of Markov chains and so forth, and inventory control is one of those. So what do we have in inventory control? Remember that our inventory tomorrow is a function of our inventory today, how much we ordered today or produced, minus what the demand was. Okay, and so here, what are we interested in that particular thing? Is we're interested in trying to optimize some form of a cost function that depends on my stock at the final day, plus some summation over either holding cost or backlog cost at all previous days with production costs. So somehow we care about something of this form. And so the central question here is, well, how do we model this? And one could pursue the agenda like what we did today, is where you looked at trying to come up with contingencies that model worst case costs. So that's one underlying choice, and that provides us some form of guarantees. An alternative choice is to develop an underlying model, a random model for our non-deterministic elements, or our demand. So develop a random model, and then focus this idea on determining policies which minimize our expected cost. Okay, so here once again we looked at expectation already, and we derived we kind of formally introduced expectation a couple lectures ago, but really this is defined as expected value, and this is going to be average cost over lots of different experiments, is what we expect. Okay, so once again these are just 2 modeling choices, and one choice need not be any better than the other choice. They just tell us different forms of things, right? And this random formulation is just a model. It's not necessarily reality. And this model really expresses our unwillingness and futility of pursuing a more detailed model. We can't express a detailed model of what this is, right? We just can't, right? I mean, maybe we can have it that measures some form of attributes, but there will always be errors in our underlying model. So all that we can think about is when designing random models versus worst case models is maybe these random models are more indicative of reality. So they give us potentially an answer that gives us a policy that's in some sense better than if we use something for a worst case. But it's not necessarily a model of reality. Okay, it's just using a different form of model to try and evaluate what we should do. And so the key that I want you to get away from over here is when we're running dynamic programming. So here's our DP. Okay, what goes into it? 2 parts go into it, right? The first part that goes into it is what is our underlying objective. Okay, that's the first part that enters in the equation. The second one is our underlying model, right? Our model of our non-deterministic output. And then the solution that comes out is the optimal solution given model. Okay? So the optimal solution given model. So there is no universally optimal solution. Rather, that optimal solution is contingent upon our underlying model. Okay? And it's also contingent upon our underlying objective, clearly. But the idea here is, given the same objective, different models are going to give rise to fundamentally different solutions with different qualities. So the derivation of an optimal choice for one model is not necessarily going to be good if reality is different than that model. Okay? The only thing that provides a degree of universality is these worst case models. Here we've derived some underlying performance, right? Some performance bounds, and now what do we have? Irrespective of the underlying model, that actually, irrespective of reality, we have some form of guarantees. When we start conditioning things further, and we start going into this case, we lose those universal guarantees, but what we gain is the ability to potentially get far better performance guarantees in situations that more resemble reality.
All right, that brings us to the end of lecture number 6. So here, what did we do? Is we introduced, we started thinking about now staged optimization with non-deterministic elements, right? And so what did we need to do is we needed to develop an underlying model for what our non-determinism was going to look like. And so once again, now optimal solutions are contingent on not just our objective and the modeling of our objective, but also the model of our non-determinism. Okay? So here what we did is we focused on just one model. We provided worst case models. So we looked at worst case non-deterministic elements. Okay? And we tried to derive optimal policies that guaranteed or that optimized worst case guarantees. Now the advantage of that approach is that this is the one type of model that we could instill on our system where we get universal guarantees, meaning that whatever performance we get in a worst case sense, we guarantee a performance at least as good as that, irrespective of what our underlying adversarial model is, or not, or our model of non-determinism, whatever reality is. Okay? So that's nice, we get universal guarantees. But in some sense, our contingency plan or optimal policy could be highly conservative so that it doesn't perform as well in situations that resemble reality. So that's kind of inspiring where we're going to go, is we're now going to start conditioning our optimal policies on more probabilistic models with the idea that hopefully those probabilistic models more closely resemble reality and hence can give us much greater performance than if we relied on these worst case models. And that's where we're going to start going to next lecture, right? But the idea here throughout, and what I think the example started to show, is we're not going to just sit in the world where we're doing exhaustive enumeration and picking the best one, as we've done on the homework and as what our coding looks like. Is very frequently what we're going to rely is on structural results. Like, can we make any form of guarantees, or can we structurally identify what the optimal policy looks like, and from there. All right, with that is the end of lecture number 6. Hope you guys enjoyed, and I look forward to seeing you in office hours tomorrow.